Hello, my name is Frank Regal. I'm currently a PhD student at UT Austin. This past summer, I worked at Argonne, where I was tasked to create an augmented reality remote operation framework to enable remote work for nuclear isotope and chemistry labs across the site. For the duration of my time in the robotics and augmented reality test lab, I was trying to answer the question about how to effectively automate and enable remote operation of hot cell and glove box work. Before I explain our solution, I will first explain what a hot cell and a glove box are, and then dive into the details of our solution later. A hot cell in the nuclear industry is typically a shielded nuclear radiation containment chamber. These are used by scientists here at Argonne to control and manipulate experiments that use radioactive isotopes. To use a hot cell, users typically need to manually move large levers, shown on the left, that are physically connected to small manipulator arms on inside of the cell, shown on the right. Glove boxes, on the other hand, are boxes used by scientists to perform experiments and control environments. These unshielded boxes are easier to perform experiments because, unlike the hot cells, the users have the full capabilities of their hands by just using gloves that seal scientists from the internal environment. What scientists would like to do is to perform their work within glove boxes or hot cells remotely. Therefore, when global pandemics arise or scientists from other countries need to use specific equipment inside of these cells not available at their home site, they do not need to travel across the world to perform their experiments. A simple solution to enable remote work in these hot cell and glove box environments is to simply install robotic manipulators inside. The problem quickly becomes then how to operate these robots so there is no productivity loss. Work has been done to provide users a 2D interface to enable them control of remote systems, but unless trained extensively, those solutions become very cumbersome and frustrate non-expert users. For example, here's one example of the latest work on how to effectively remotely operate a robotic system. As you can see, there are multiple windows, an immense amount of buttons, and even multiple joysticks and keyboards. This can overwhelm a scientist very quickly. Robotic manipulators can be programmed to perform specific tasks, but in realistic settings, the experiments being performed in hot cells and glove boxes are always changing. Therefore, making unstructured task automation almost infeasible, as someone would need to reprogram the robots for every single experiment, which could take days. So how can we enable users to remotely perform their experiments in a hot cell or a hot box outside of the lab? One solution we envisioned and brought to life this summer is the combination of a hot cell and a glove box, coined a hot box. The hot box consists of two robotic arms that are controlled by the user naturally using their own hand gestures that are tracked and visualized with an augmented reality headset. You can see this on the left, and you can see the augmented reality headsets on the right. In this video, you can see preliminary work done earlier this summer to prove the concept with one physical robotic arm in the hotbox being controlled by my hand gestures tracked through the augmented reality headset I was wearing. The full screen video is the first person view of myself manipulating a holographic replica of the physical arm, and the corner video is showing a third person view of what everyone else around me sees. To bring this idea into reality, we combined a few existing technologies to make it happen. We took a HoloLens 2 augmented reality device and programmed it along with two Kinova robotic arms using Unity and ROS to enable what you saw in the previous video. What is a HoloLens 2? A HoloLens 2 is an augmented reality device created by Microsoft that augments a user's physical world with holographic overlays. The device then lets you interact with these holograms and provides developers tracking capabilities to capture position data of the hands, eyes, and head. To develop on the HoloLens, you need to use a game engine. For this project, we chose Unity as our development platform. This software is what is used to make popular video games. In our case, it enables us to access the data streams from the headset, provide users visualizations, and communicate with the robots directly. When designing the new hotbox, Kinova Robotics Gen 3 arms were chosen. These arms were selected for their 7 degree of freedom capabilities and software development flexibility. To communicate data between the HoloLens and the robotic arms, middleware software called ROS, or the Robot Operating System, was used. This is an open source library of software that is a standard in robotics research and development. Using all the previously mentioned components, we configured them in a way to make remote teleoperation of the robotic arms from the HoloLens 2 possible. You can see here an overview flowchart of how the data flows from the HoloLens 2 over a local network through a series of software packages to the robotic arms and then back to the HoloLens. The results of these techniques ultimately answer the research question and enable scientists to remotely operate robotic arms placed within a hotbox. The solution we developed allows remote manipulators to mimic the natural motions of the user's hands and enables simple replication and improvements to safety for scientists. This photo, taken from the HoloLens, shows the physical hotbox on the right-hand side and the holographic replica on the table to the left. Users can walk around and position the holographic replica hotbox anywhere they would like. By just pinching your fingers on the end of the virtual robotic manipulator and then dragging, the physical robot arm will follow. Next steps to apply this research would be to include video feeds and virtual fixtures in the user's environment. This will provide more situational awareness to the user and assist the user with complex manipulation tasks. Finally, the integration of a virtual point cloud would allow users to see 3D objects remotely, again for better situational awareness. Research should also be performed to understand the best gesture control methods. I would like to thank everyone for listening today and give a special thanks to my supervisor, Dr. Young Park, and all others I interacted with this summer. Thank you.